are in listen-only mode.
Good afternoon, everyone. My name is Kendall Trump with Grain Journal Magazine in Decatur, Illinois. Welcome to today's webinar, Measuring Air, How and Why, presented by Kice Industries. In today's webinar, Kice Industries will discuss how to use an air measuring kit to measure the static pressure and velocity pressure of your system. You will also discover what happens with varying fan speeds and damper settings and realize how it relates to dust control or pneumatic conveying systems at a facility. Our presenter will cover why the process of measuring air to determine CFM and velocity in a system at any grain facility is important for collecting systems operating effectively and efficiently. Finally, you will learn how properly performing air readings provides improved product quality, extended equipment life, saves energy, reduces emissions and housekeeping, and increases overall safety. Today's presenter is Lonnie Glenn. Lonnie is the Technical Sales and Quick Ship Manager at Kice Industries. He has been with Kice since 1998 and has developed and implemented the Kice Quick Ship program, and in 2001 transferred into Kice Technical Sales and System Design. Lonnie became a regional sales manager for Kice in 2015 and most recently is now technical sales support for all the Kice regional sales managers and is back to his roots overseeing Kice Quick Ship. Most recently, Lonnie developed a Kice Centrovac design guide for Kice Industries. Questions may be submitted to us today by typing them into the questions box at the right-hand side of your screen at any time during today's webinar. We will be answering your questions during a live Q&A session following the presentation. As a note, this webinar is being recorded and the recording and presentation slides will be sent to all registrants. At this point, Lonnie, can you please do a voice check?
Voice check, this is Lonnie Glenn.
Great, we can hear you perfectly. And can you also please show us your screen?
Did that do it?
We're not seeing it in slideshow mode at this point.
And there we go.
We're still seeing the PowerPoint program, but we're not seeing the... Oh, perfect. Ladies and gentlemen, here is Lonnie Glenn.
Thank you, Kendall. Well, as I start this, I will start with a couple things. I apologize if there are engineers in the audience because we're going to talk about how we measure air. That's different than the way engineers measure air. They're very scientific and they do a great job of doing it. A lot of times we're trying to see if there's enough velocity in a line to get it from point A to point B, try to help with troubleshooting on fans. And so we take a little bit different approach, much more simplified approach. So I just don't want to offend any engineers in the audience. But as Kendall mentioned, I'm going to talk a little bit about measuring air, how to do it, and why it's important. Applications for air, there's so many, and most grain facilities and milling facilities have a lot of these processes. It could be grinders, it could be granulators and hammer mills and pellet mills, cooler systems, pneumatic conveying, both pressure and vacuum. An obvious easy one is dust control as an application for air. Reasons to know how to measure air volumes and reasons you need to know why and what the air volumes are. It's to know if your equipment is operating efficiently. It's trying to get the best operation that you can for the least amount of horsepower, or at least not waste a tremendous amount of horsepower these days. Sizing new equipment. You have a new facility or you're changing your facility, you're adding dust collection. How much air do you need? How much aspiration do you need? How much air do you need for conveying? All these reasons for measuring air volumes and helping to determine air volumes can help you in sizing new equipment. When is it important to replace equipment? A fan, typically maybe a material handling fan, grain that's going through it, or grain that sees a lot of bran or screenings. Fans that see the screenings and bran, they're going to wear out. That rotor's going to thin down. It's just not going to move as much air. Maybe you have holes in the cyclone, bags in the filters. It'll help you kind of see where that air and that velocity and that pressure is going. And probably the last and anymore is probably about the most important, record keeping. People want to walk into your plant and they want to see numbers. They want to see you've been taking care of this. You've been keeping your air emissions down. They want to see that. They're going to ask for that. This is a very simple diagram. Basically, it's my explanation on a dust control system. We are looking for the sum total of the CFM that we need for the system to handle. In that case, in this diagram, it's in red. I've got 1, 2, 3, 4, 5, 6 different pickups: cyclone, belt conveyor, bucket elevator head, bucket elevator foot, boot, a bin, and a screw conveyor. Each one of those have a line size come off of it, or the equipment is known to have this much needed CFM. And then in blue, that is the static pressure. But back to the red, I sum total all of the pickup points. 180 from the cyclone on the far left, 325 from the belt conveyor, 520 from each, or from the head, 325 from the boot. All those total up to 2,425 CFM. But on the static, it's not a sum total of all the static runs. It's basically the longest, highest static pressure run of the system. So in my diagram, I've got 3.5 inches on the far left. I'm saying, as an example, there's 3.5 inches lost from that hood or from that cyclone back to that first branch fitting. There's another 1 inch of column between the first branch fitting and the second. 0.7 between the second and third, 0.5, 1.3. Then there's another 2.5 to the cyclone. The cyclone has 4 inches of water column, and I've allowed for a 1/2 inch of water column on the clean air ducting side. So when I add up all of that static, the 3.5, the 1, the 0.7, 0.5, 1.3, 2.5, the 4, and finally the 0.5, I get 14 inches of water column. So if you ask me, or if you ask anyone to size a system and you said, I am looking for a dust collection system that can do 2,425 CFM, and I calculate that we need 14 inches static pressure, that's going to give them a very good start on what they are, at what you need. Common terms that we'll be using include, whoops, sorry about that. Common terms we'll be using in this and in measuring air. A pitot tube. A pitot tube, we're going to see a picture of one in a minute, but it's a device used to measure both the static and the velocity pressure. Air measuring kit, we throw that around. Basically, it's a kit we can supply, others can supply, that contains the components that you need to measure air, including a pitot tube. Probably multiple magnehelic gauges, maybe a tubing, drill, charts, calculator, that kind of thing that'll help you get the job done. Those magnehelic gauges are basically pressure differential gauges. Usually there's a 0 to 3 inch for measuring velocity pressure, and in a typical system maybe you need 0 to 20 inches for a dust control system. For a high static system you might want to get one that goes to 100 inches or 50 inches for water column. So those are different devices that are used to measure pressure differential. Velocity, we're going to use that word a lot. Velocity basically is the speed of the air, and it's measured as feet per minute. So when I talk about velocity, I'm referring to the speed of the air measured as feet per minute. Volumetric airflow rate. Again, the short version is CFM, cubic feet per minute. How much air do I need to move, and at what velocity in feet per minute? And that's going to help me get to the results that I'm looking for. Duct velocity. That's inside that tube, whether it's a 3-inch tube, whether it's a 16-inch tube, whether it's a 24-inch tube. It's how fast air and dust and product is flying through the duct. It's typically measured in feet per minute. From what I've learned from the Kices over the years, grain and other materials, grain dust typically flies at about 3,400 feet per minute. Lighter dust might be as low as 2,800. We tend to think of grain dust when we design systems around 36 to 3,800. Kind of gives us a little wiggle room. If I were conveying wheat typically conveys, whole wheat typically conveys around 4,200 feet per minute. So we might size it for that. If I want to have a little safety, I might go 43, 4,400 feet per minute. So the duct velocity is important to us to keep that dust, that product, in suspension. Here's a picture of a typical air measuring kit. Again, it shows a couple gauges there. There's the pitot tube, a little hand drill, some tubing, a little diameter tape measure. Usually we put in a few extra screws, a tip cleaning device for the pitot tube, that kind of thing. So it comes as a complete set that you can keep handy. Here's a picture of a pitot tube on the upper right. And on the far right, you see the total pressure port. There's a little hole in that pitot tube, and that's where the total pressure is being measured. If you look at a pitot tube along the side there, there's a bunch of small holes in the side of it. That's the static pressure port. As we go right to left, there is a total pressure connection and a static pressure connection. So on a pitot tube, they're all the same. There's a total pressure port, a static pressure port, a static pressure connection, and a total pressure connection. And then you have some tubing, and then you have your magnehelic gauge. This is typical of a magnehelic gauge you might see measuring a high static system, since it's going up to 60 inches of water column. But there's a high pressure connection on it. There's a low pressure connection on it. They're marked on the side of the magnehelic. I think they're marked on the back. So it's pretty easy to tell which is which. Back to some more common terms that we're using. Static pressure. What is static pressure? Well, static pressure is the pressure that's used to overcome the resistance on the inside of the duct. It's the pressure loss across the hood, across the cyclone, across the filter, across the 3-inch ducting, across the 3-inch elbow, across the 16-inch branch fitting. All of those add up to our static pressure. It's usually the longest, smallest diameter run, but not always. So if you're doing a dust collection system, we like to look at the whole layout and work backwards until we find that highest static system, and that's what we base our fan selection on. Velocity pressure. It's the pressure required to accelerate all that air from basically static sitting there to 4,200 feet per minute. It's air traveling at a given velocity. Basically, it's just a way to calculate velocity by getting the velocity pressure. The total pressure is the sum total of the static and the velocity pressure. So again, static pressure in that earlier example was 14 inches. If we wanted to do it at 4,000 feet per minute, that's basically 1 inch of water column. And then the other thing that's important is to know the area on the inside of the duct, and it's measured in square feet. So you have to do a little math, come up with a diameter of the inside of the duct. You can cheat and take the OD, but you give up a little bit if you don't use the ID, and then you convert that to square feet. Here's a vector representation of what we just talked about. I'm going back for a second. Static pressure, velocity pressure, and total pressure. Static pressure is the forces exerted on the inside of that tube, on the inside of the steel, the aluminum, the stainless, whatever your duct might be. The velocity pressure is how much it's taking, how much energy it's taking to move that air through the tube. And then the total pressure is the sum total. Total pressure equal SP, static pressure, plus VP, velocity pressure. Before we go much farther, let's just talk about common terms away from the air side that are still necessary to talk about how we fix things. Air to cloth ratio in filters. It establishes the design capacity for a baghouse filter. You can read that there. It's part of the notes, but I'm going to go off script for a minute. I had a call today from a customer who said, Lonnie, I have an M14410. That's a modular 144 bag filter with 10-foot bags. He said, how much CFM can this handle? I would love to give someone a definitive answer when they ask that very specific question, but it's difficult because once you take the bag area, in the case of my example here, I figured it had 1,555 square feet of filter area, and he wanted to use 15,000 CFM. So 15,000 divided by 1,555 is 9.65 to 1. In my example earlier today, I calculated the area. I think it was like 1,696 square feet. And I said, now it depends on what air to cloth you want to use. How much are you loading those filters? Rule of thumb that we use, 7 to 10 to 1 for elevators, cleaning houses, general suction. I think the standard, and this goes before me, standard used to be closer to 12 to 14 to 1. But people were changing filter bags every 6 months. And then they said, hey, if we have lower air to cloth ratios, we can get away with changing those bags once a year, once every 18 months. And that became more the norm. Again, secondary collectors or high humidity systems, as a rule of thumb, we use 7 to 1. For filter receivers, for central vacs, for bin vents, we say 5 to 1 as again, a rule of thumb. So air to cloth ratio comes into play. It's important for you to know how much CFM you have and how much bag area you have. And really the one thing that jumps out at that is if your air to cloth is too high, you're going to have very short bag life. Then there's can velocity. And there's two terms that kind of float around here. Can velocity is the velocity measured inside the filter in the open space below the bags. But interstitial velocity is that velocity measured between the bags. It's going to be higher because there's less area. We have a little chart, and I must admit we've gotten this from somewhere. I don't know that we developed this, but a bulk density and can velocity. If you have a product that's 30 to 50 pounds per cubic foot, a can velocity of 300 to 360 feet per minute below the filter bags, it's probably going to work out fine for you. But if you have a product that's, say, 10 pounds per cubic foot, it's just going to hang up in the filters. It's never really going to settle unless you have a can velocity of 120 to 150 to 180 feet per minute. So it depends on your product for the can velocity that you need. So now we get into kind of the meat of this, if you will. Basic formula, Q equal VA. To determine CFM, Q equal VA. ACFM, or the volume of air, is Q, the velocity in feet per minute, which we'll do the math on, and A is the tube internal cross-section area in square feet. So it's CFM equal velocity times area in square feet. So we follow a few basic principles here. First, we got to obtain the velocity of the air. Then we have to obtain the area of the duct, the pipe, the tubing, the fitting at the point of measurement. And then it's pretty simple. We multiply the velocity times the area to determine the volumetric flow rate, or CFM. And again, I'm going to mention this a little bit downstream of this, if you will. Why 5+ pipe diameters downstream of a fitting? Well, air after an elbow or a fitting, it becomes what they call turbulent. It's bouncing off the edges, it's bouncing off the sides, it's all over the place. So if we go as many diameters as we can, and engineers will say 20. In our world, in milling and in grain industry, in the plastics industry, where everything is so close together, we're lucky to have 5. We may not have 1, but we try, and you guys try, and we know that. So we just have to look for a spot that's a little bit downstream that lets your air, what they call, become more laminar. It evens out as you get a few pipe diameters downstream after an elbow. It certainly makes the measurements more accurate because we're trying to measure the center of the tube in the way we do it, whereas an engineer will measure the inside edge, and you'll come back a few degrees, few fractions of an inch, and measure again and again and again and again, and then average those out so that he has more of a true idea. We're typically measuring in the center of a line. So again, as we move forward, I say 5+ pipe diameters. I'd love 10. I'd love 20. We'll take what we can get to help you try to figure out the air. Typical air measurement points. I've highlighted several spots that you can get your outlet static pressure and a velocity pressure reading. And if you look at the diagram on the left, it says 5 times the diameter minimum. Okay. The one on the lower, again, after 5-time diameter straight run, that's a good spot to measure that inlet static pressure and the velocity reading. On the right, again, first one is after an elbow, after the fan, after an elbow, come down 5 pipe diameters, let that air get laminar again, and you can measure your outlet static pressure, your velocity pressure. Going into a fan, if you have that 5+ pipe diameters, that's a good spot to measure that air. And again, there's another one at the lower right, optional velocity pressure reading point. Again, it's a minimum of 5 diameters between elbow A and elbow B. Now, I've said this is good places to measure air. Here's some places that are not so good to measure air. Starting from left to right, I kind of got a call out to those locations. Right after an elbow, not a good place. Right after elbow at the inlet of a fan, not a good place. Again, right after an elbow on the right, and right after the fan, the air is very turbulent. It's all over the place, not a good point. Again, right after the elbow in a couple of locations. And then one, it's too short of a straight run after the elbow. It's just not enough linear distance to get laminar again. So that reading is probably going to be different than some of your other readings. That air is bouncing back and forth from edge to edge, or maybe more of it is on the inside edge of the tubing and rather than in the middle. And using Kice installed equipment as an example, I'll pick a few more places to show not good and good locations. The cyclone on the left, I've got a call out to not good location, difficult to measure the area. Again, when you have something that transfers from round to rectangular, and then you drill a hole in it and you put the pitot tube in it, it's going to be difficult to really figure out where you're measuring. So in a transition in a rectangular to round, or even a round to round, it's difficult to find a good point because you're going to need to know that area. The other not good location is right after the elbow. A couple good locations, again, you can see coming out of the elevator, it goes up into the cyclone. There's a good spot to measure that air right before that 90. Coming out of that cyclone, going into the fan that's most likely indoors, there's a good spot to measure that. The Kice fans on the right, again, elbow and elbow. And this was our old fan brochure, but it's probably not the best way to have ducting coming into a fan. But again, inside mills, inside elevators, you get the space you get. So in this case, neither one of those spots is a good place to measure air. Air's too turbulent. There's not enough straight run. It's just bouncing back and forth. You'll get a measurement, but it may not be the best measurement that you can come up with. So, by the book method, again, my apologies to engineers, but everything starts with safety these days. I've said select a location 10 pipe diameters away. Some of the newer books call out 20. They'll typically drill 2 holes 90 degrees apart, and our engineer just recently let me know that that's changed, and an engineer who's doing it by the book will actually drill 3 holes 60 degrees apart and take traverse readings of that tube across 3 planes of that duct. And then they'll connect the pitot tube. They'll insert it. They want to record the temperature and the absolute pressure. They'll traverse the tube, recording the static pressure or velocity pressure readings at published insertion depths. They'll read it in 2 or 3 planes. Then they'll calculate the velocity. They'll average the velocity. They'll calculate the tube area in square feet. And again, it goes back to my Q equal VA. They'll multiply the velocity times the tube area to get to the CFM. Again, that's a very short version of by the book, but it's a very accurate way to get that kind of air reading. The reality method is more what we use, what you might use in your facility. Again, safety first. Try to select a location about 5 pipe diameters away. You drill a hole. For the most part, you just need to put your hose perpendicular to that hole over the flow, and your pressure gauge for static pressure is going to read. Okay? If you use the pitot tube, you center that tube inside the duct, and there are inch marks on a pitot tube. So if you go, I always tend to go to one end, and let's say it's an 8-inch tube. Well, I'm going to insert that pitot tube to 8 inches. I kind of verify that it's 8 inches. Then I'll back it off to where I get that 4-inch mark, and I feel like I'm pretty much in the center of that tube, and I can record my reading. So static pressure is relatively simple. You drill a hole, you put the hose over the hole, hold your gauge somewhat level, and you've got your static reading. Reality method for estimated airflow measurements. Again, safety first. I give them my 5 pipe diameters again. You drill a hole. You connect both tubes to both ports on the pitot tube. Both the total pressure port and the static pressure port. You record the VP at the center of the duct using the pitot tube. So we drill a hole, we insert the pitot tube, we try to find the center, and we look for that velocity pressure reading. Usually we're using a 0 to 3, a 0 to 5 gauge. It's the smaller of the 2 gauge measurements. Now what we're going to do is take that velocity pressure reading that we get from that gauge. We're going to convert that to a velocity. And the next few slides will show you some of that charting that goes on. But also, because we want to try to get to an average, we will multiply our velocity times 0.9 for 6-inch OD and smaller ducts, and by 0.95 for ducts 8-inch and larger. And that gives us what we call our estimated average velocity. So now we have our estimated average velocity. We determine the area in square feet. Here comes the math. If it's in square feet, you take the area of a circle, which is 3.14 times the radius squared, or 0.7854 times the diameter squared. That'll give it to you in square feet. If it's in inches, a little more work to do, because 144 square inches equal 1 square foot. 3.14 times radius squared divided by 144, and that gives you the square feet. Now, Q equal VA. CFM equal velocity times area. We do that math, and we have a pretty good indication of our CFM. Pictorial guide here, measuring static pressure. I've inserted the pitot tube in a drilled hole, this piece of plexiglass. It's somewhat centered in the tube. I take my gauge, you hold it, try to hold it level, make sure it's zeroed out before you put it in. You should be able to get your static pressure reading. If you wanted to do an easier route, unhook it from the pitot tube, put that hose right up against that hole in the sidewall of the tubing, and you should get a very good reading on your static pressure. Again, velocity pressure is total pressure minus the static pressure equal to velocity pressure. Okay, and I've said that 2 or 3 different versions of that throughout this. But total pressure is minus the static pressure gives you the velocity pressure. Measuring velocity pressure, again, by the book, the one on the left, both connections hooked up. You zero out the gauge, you hold the gauge level, you measure in 2 or 3 planes, you traverse readings, then you got to average it out. The reality is most people, myself included, will try to get our pitot tube in the center, and we'll get a reading at the center of the duct. And that's what we use for when we start to do our calculations. Now, going to some math, finding velocity. Example 1 in the red. I got a velocity pressure reading of 1.1. I can look at a design chart that Kice publishes. This happens to be from the Industrial Ventilation Manual. And if you look closely, VP 1.1 equal V, or velocity, of 4,200. 4,200 feet per minute. Example 2. I do my velocity reading and I get 1.75. I look there and my velocity is 5,298. My example 3 in blue, my velocity reading is 3.6. I look at the corresponding velocity, got 7,599 feet per minute. Again, this is all at standard air. Calculating velocity, which is basically 4,005 times the square root of the velocity pressure. Now, finding volume from these 3 examples. Example 1, we're going to assume that the tube was 12-inch OD, and by looking or doing our math, we've got a square footage of 0.7854. So my velocity that I measured, 4220, times my average factor of 0.95, since it's above 8 inches, my average velocity is 4,009 feet per minute. So 4,005 times 0.7854, got a math error there, 3,149 CFM. Example 2, same 12-inch tube, same area, 0.7854. My velocity was 5298. My average correction factor of 0.95. My velocity, 5033. Again, math error here, I apologize. 5033 times 0.7854 is going to give you a volume of 3952. Example 3, I think I have this one right. 12-inch tube, 0.7854 square feet, my velocity of 7599 times my average correction. My average velocity is 7,219. I use that 7219 times my area, gives me a volume of 5,670. So again, I apologize. My example 1 and 2 both have some math errors. Example 3 has the right numbers involved. Now, we're taking all these readings based on standard air. And I will tell you, I'm not an engineer. I'm not sure I could explain very much of this. If you ask questions at the end over this, you're probably going to stump me. Typically, we calculate the air velocity from velocity pressure. We just talked about that. That's it. We're basically doing this at 70 degrees and sea level and a barometric pressure of 29.92 Hg. But we should be correcting for actual conditions because it's ever changing. Wichita, Kansas is around 1,350 feet above sea level. A cooler application or a pellet mill application is going to be a lot hotter. Maybe it's in the middle of the summer in your mill or your elevator and it's 100 degrees. Well, we need to make some corrections that are different than standard air because it's going to make a difference in our CFM. So that velocity is velocity times 1,096.7 times the square root of the velocity pressure divided by the air density. So with all those numbers, I'll move to this screen. We utilize a sheet that helps us determine air density correction factors. If I input in my spreadsheet, and you can get these online, I'm sure, a 70-degree temperature, 0 feet, my inlet air density is 0.075 pounds per cubic foot of air. That's what that air weighs. Okay? Now, if I correct that same spreadsheet for 120-degree temperature air and 1,350 feet above sea level, my air density corrects to 0.06532. So there's that correction. That's what the difference is made between 70 degrees and 120 degrees, and 0 feet above sea level and 1,350 feet above sea level. So let's remember a couple numbers here. 0.075 was my standard air, and 0.06532 is my corrected air. We're going to do a couple examples here. The first one is based on 70 degrees and 0 feet above sea level. That calculation for velocity was 4,005 times the square root of the velocity pressure. We had data sheets that helped us correct that and show us that on a few slides earlier. So V equal 4,005 times the square root of the velocity pressure. Let's say we measured 1 as the velocity pressure. 4,005 times 1, 4,005 feet per minute. We average that at 0.95 for, say, that 12-inch duct, and we get an average velocity of 3,804 feet per minute, 3,804.8. Again, CFM equal V times A. CFM equal that 3,804.8 times the area, 0.7854, gives us a CFM of 2,988 if we were just measuring the air without taking into account any correction factors. Now let's correct it for the reality, 120 degrees and 1,350 feet above sea level. And these numbers change. Again, you might have 80 degrees. You might be 4,000 feet above sea level. You just have to correct that density for that. That calculation is a little different. Velocity equal 1096.7 times the square root of the velocity pressure divided by the air density. I've done that calculations below. Velocity, I'm going to the second line, velocity equal 1,096.7 times the square root of 1 divided by 0.06532, which is that number we got from the last slide. Velocity equal 1096.7 times the square root of 15.309. 1,096.7 times 3.9 gives me a velocity of 4291. Then I average my velocity, again because it's a 12-inch line, and we know we're using 0.95, I get a velocity of 4,076.5 feet per minute. CFM equal V times A. CFM equal my average velocity times my area. My CFM is now 3,201. So if I don't correct for that, I'm saying my velocity is about 4,005 feet per minute, and I'm about 2,900 CFM, call it 3,000 CFM. But if I do correct for the actual conditions, 120 degrees F and 1,350, my average velocity is closer to 4,076, and my CFM is actually higher. It's at 3,200 feet per minute. Not a huge difference. 200 CFM doesn't make a big difference in the scheme of things, but a whole bunch of those can overload your filter fairly easy. A lot of math there. Again, in the last few slides, I just wanted to give you an idea that we tend to measure air in standard conditions. We probably should be spending more time measuring it in actual conditions to get a better reading, give you better information. So as we kind of start to summarize here, what do you know? What good is it? Well, you have known data, you can compare it to calculated data. I'll use me for an example. I calculate a system for you, and I said it needed 2425 CFM at 14 inches water column static. That's what I said it was going to do. Well, you measure the air in problem number 1, and you've got the total air instead of 2425. You measure the air at 4500 CFM. Well, now Lonnie calculated it for 2425 at 14 inches, but somehow I'm getting 4500 CFM. What's going on? Well, I can tell you probably got short bag life, you got high air to cloth ratio, you're dusting out in the filter possibly, maybe you got line plugging, lots of different things can be going on. You got to ask yourself what changed, what was added, what was taken offline, something open, full open that's not supposed to be. So you can start to kind of dial in on what the issue might be. Following that same example, issue or problem 2, your air lag, maybe in a mill, no longer has the capacity it used to. Maybe in a grain elevator, it's, hey, I just can't push that dust all the way to the top of the elevator anymore. I used to be able to do it just fine. Well, maybe your fan or your power unit's not able to provide adequate static pressure, and conveying line can't handle the load. Gives you a starting point. Are your belts loose? Over-amping. And I always ask this, and I always have to apologize when I do, is the fan going in the right rotation? You'd be surprised. A motor got changed, fan rotation, they thought it was right, and a fan running in the wrong direction will pull air, just not near as much. So is it a worn fan? We talked about that earlier. We get calls for customers who have fans in material handling applications that have just worn that rotor down to a nub, and they just can't move as much air as they used to. Where's the choke point, leak point? Maybe it's the inlet filter on the APU, maybe it's the filter bags on the filter. Last problem, your grinder or mill is getting too hot. You're starting to burn up bearings. Maybe you get some scorch marks. Well, maybe you're not pulling enough CFM and static pressure to reduce the heat at the mill. So again, it's a starting point. What's been relocated? What's the feed rate? Fan rotation? Where's there a choke point? There's a lot of different things, but you can start asking yourself, I knew this worked when, and Bliss or Roskamp Champion or whoever had the hammer mill said it was supposed to take 3,000 CFM and my mill takes 8 and the air system takes 12. Well, I measure air, I've only got 10 inches of static. At least you got a starting point to figure out what's the next step. The last one, almost to the end here, why is this information important? Well, again, you want to make sure your system has adequate velocity so that that dust goes all the way through the line. So you have to keep it relatively equal even as you add branches. Proof of performance, airflow and static measurements. You can measure air at different points in your system and find out I've got 4,005 feet per minute, which we believe should carry dust back to the filter. In this branch, I've got 2,400 feet per minute velocity. Well, Lonnie said it takes at least 3,600. I'm probably not pulling enough air here, and dust is dropping out in that line. So it kind of gives you a check and balance system. Again, records becoming more important every day, and when to follow up when they get out of the acceptable range. So if you know this information, you can start to keep some history on it. And it's always nice if you have some assigned, trained personnel responsible for the system. Give them the tools, give them the time, give them the training to use an air measuring kit, and then they can help you when you decide to make follow-up actions. General good practices: increase the line size as needed to keep good velocity in the line back to the filter. And we'll show this in just another slide right quick. But it reduces resistance and it keeps the dust in suspension. Use lockable dampers or slide gates. Mark them, even if it's just a Sharpie mark. At least you can say, this is what it was doing when it was working. Let's go back to that point. You got to allow some free air. You can't pull against a closed system and get any kind of movement of air. So you've got to have some free air. You got to make use of natural air currents. Seal up any leaks in the system. If you have enough points where air leaks out or air gets pulled in, you may not have enough air at the end to pull that dust through the line. And they'll add up. Purchase and learn to use an air measuring kit. Obviously, Kice has one. I'm sure that there's lots of folks who probably do. You learn to use it, learn to measure with it, and it can give you some good data. And use care when putting your pitot tube into the conveying line. Those small ports can plug. Now, we provide a little clean out tube with it that can kind of clean out some of those tubes, but if you put it in a flour conveying line, chances are you're going to pack enough flour in there, it's not going to come out. So just be aware of where you're putting your pitot tube in the conveying line and in heavy dust control lines. Good design, starting left to right. My velocity is at 4,000 feet per minute. I add a 3-inch line, so that makes my two joining lines a little hotter. I add another line, add another line, and ultimately by the time I get to the fan, I'm at 3776 feet per minute. So that's probably a good spot to convey dust back through the system. Everything's in suspension. You're not really wasting any horsepower. Bad design, and unfortunately we see this a lot, and I'm sure you guys have this some of you have this in your facilities. Somebody ran a straight tube, whether it's an 8-inch tube or a 12-inch tube or whatever size tube, all the way down the run. And then they branched off with that. Well, that area, in this case, that area of an 8-inch tube is not going to have very high velocity when you don't have very much airflow. Again, going left to right, I've got that 3-inch tube at the very end. It's only 180 CFM. Even after I pick up the 4-inch tube, and now I have a sum total of 180 plus 328, call it 508 CFM, my velocity in that 8-inch tube is only 1,500 feet per minute. As I've stated, that's not enough to keep it. So what's it do? It lays out in the line until there's enough closed off area so that the remaining area can convey that dust down to the next point. And so you kind of look at this example and you wonder, this is why you have dust lying in your dust control lines, and you thump them and they sound solid. And that's probably a good indication of what's going on there. Additions and deductions both without rebalancing your system. Let's say you add an 8-inch line near the front end. Well, air takes the path of least resistance. It's going to pull most of its air from there, so you're not going to have the velocity at the far end to convey that. And it just starts to build up in those lines, starts getting heavier inside those ducts. But your 8-inch at the very end that you just added has got all the air in the world that you need. Deduction. Not as bad, but it's a horsepower waster. You close off a 4-inch cap. Something moved, piece of equipment left, don't need it anymore. You just cap it off. Well, you're going to have more air now because you didn't do anything with the fan. The fan still wants to pull that much air. It's going to pull more CFM at a higher velocity from each of the other pickup points. And if you increase it enough, you're going to start to pick up good product. You're going to hear the sound of the corn inside that line, the wheat inside that line, the plastic pellets inside that line. And then you're going to go, why do I have all this noise? Why am I losing good product? Because you're taking it to your dust control system. So kind of backing up, there's good designs, there's bad designs, there's consequences whether you add something or you deduct something. And that's if you rebalance your fan after you close something off or add something, fantastic. That's the proper way to do it. And then really kind of wrapping this up, once you're done measuring the air, leave the the drilled hole open. Usually it's not so large as to affect the system, but it can be a point where foreign matter can enter. Or you cover the hole. It closes a leak point. It doesn't allow foreign material in. That can be a self-tapping screw. It can be a rubber plug, a dab of silicone, some duct tape, some HVAC tape, or an air measurement label. And at Kice, we have these magnetic labels that have static pressure, velocity pressure, measured by and date on it. So you can write that information, cover that hole, and if it's aluminum or stainless, it may not stick, but you can tape it on nearby so the next person knows, hey, we measured this at this date. This is what we measured. Let's try to get back to that. Closing comments. It's not difficult to take the air measurements with the right tools. It'll help you when you call into Kice or anybody else and say, hey, my fan is doing this. This is my CFM. This is how I got it. Help you minimize downtime, and the benefits are great. Product quality benefit, product recovery, extend equipment life, energy, reduce emissions, reduce housekeeping, which is becoming more and more of an issue every day, and keeping plants running and out of trouble. So with all that said, I will just hand it back over to Kendall, say thank you for taking time, and if you have any questions, Kice, myself, will be happy to answer them. And my email is shown here at the bottom, lglenn@kice.com, and my phone number. And so, Kendall, I'll turn it back over to you for any questions.
Thank you so much for a great presentation, Lonnie. That was very informative. We do not have any questions at this time. To our audience, if any questions do pop up, please feel free to send them to our presenter using the email address that is currently on screen. That is all that we have for today. I want to thank Kice Industries and our presenter, Lonnie Glenn, for a great presentation today. I also want to thank you all for attending and wish you all a great day.